Hello everyone. Today I'm going to share with you what we are currently working on in collaboration with the microfluidic cluster microfluidic cluster from the Vascular University. It is the use of nanoparticles to enhance the response of an LMR biosensors. The single presence optical fiber biosensor have already been used for many biosensing applications. For example, for the early diagnosis of immunosensor diseases or the detection of C-reactive protein, which is associated to inflammatory processes, among others. And recently, we have been very focused on the transition to planar LMR biosensors. This is because planar waveguides have proved to be easy to manipulate structures. They are also robust and they are cheaper than optical fiber. And many efforts have been done in order to enhance the features of the resonance that we obtain with planar waveguides. However, there's still a lack of sensitivity. Sorry, can you speak here? There's still a lack of sensitivity in some applications, in particular when very low limits of detection are required. And this is the case of the vascular endothelial growth factor, the VEGF protein, that is an important protein associated to angiogenesis process. And it is also related to tumor growth and ophthalmologic, inflammatory, and cardiovascular disease. So the strategy that we propose in this work to detect this biomarker is the amplification of the signal of our LMR sensor by using nanoparticles in a sandwich assay. The first thing we need to do to achieve this goal is to deposit an intermediate layer of gold over the surface. It's a surface that was previously nice. And then we deposit titanium oxide thin film by atomic layer deposition to generate the resonance. Then the chip is inserted inside the microfluidic cell. The setup that we are using to carry out all the experiments consists of a light source that transmits light to one edge of the cover slip, and then the output light is polarized and transmitted through another multimode fiber to the spectrometer. The chip is placed into the microfluidic cell that is connected to our static pump. So now let's focus on the detection assay. And the first step is to activate the surface for 1 minute with plasma. And then the chip is inserted into the cell, and the immobilization of the captured antibody is carried out for 1 hour. And this captured antibody is very specific to the analyte, to the VEGF protein. After that, the surface is blocked for 10 minutes to avoid specific interaction. And then a solution containing the VEGF protein is flowed through the system, and the protein binds specifically to the capture antibody. And until this point, we will have a label-free biosensor. The problem is that our sensor is not able to detect the protein at the concentration that we are interested in. So this is why we perform the step 5. When a biostimulated secondary antibody is injected to the system, and this secondary antibody is also specific to the analyte. And this is why we make this sandwich, you can see here, that is labeled with a biogen. Then, and finally, a conjugate of gold nanoparticle with estreptaline is injected, and the estreptaline binds specifically to the biopsy. And this is because these molecules are very specific to each other. This is how we amplify the LMR signal that we obtain because of our analyte, that is the VEGF protein. And all the steps in this assay are monitored to follow the position of the LMR in real time. And also after each step, there is a watching step with PBS buffer to establish the baseline and also to watch for the system. The first VEGF concentration that we tested was 1 microgram per milliliter. And as you can see here in the green line, okay, as you can see in the green line, there is the resonance achievement of about 32 or 34 nanometers, that we consider is important response according to our experience with label-free LMR biosensors. Then we started to decrease the VEGF concentrations, and the achievement of the resonance due to the nanoparticles were lower as we were expecting. And the sensor was able to detect a concentration of VEGF as low as 0.1 nanograms per milliliter. Of course, we need to obtain more data to build the characteristic curve of the sensor. Finally, in this experiment, what we did was to test the specificity of the gold nanoparticles, and we made flow through the system the conjugate nanoparticles after each step of the assay. And as you can observe, there is no, the resonance did not change its position because of any inspecific interaction of the gold nanoparticles, but only after the binding with the secondary antibody, we saw achievement of the resonance due to the gold nanoparticles. So this means that the nanoparticles are not binding to any other element of the cell that we are performing. So this is a very young research, and these are all the results that we have by now. But as conclusions, we can say that gold nanoparticles were used for the first time to amplify the response of the LMR sensor, and VEGF detection in the range of 0.1 to 1 nanogram per milliliter could be useful in the diagnosis of different types of cancer. That is actually the best response that we obtain in this range of concentration. Then this strategy has the potential to be studied with nanoparticles of different size and materials, for example, polymeric nanoparticles. And finally, these preliminary results open a complete new range of applications for LMR biosensors that were not available until now for us. And so, thank you so much.
Thank you very much. And now we have a time for questions. Now, you prefer you can ask also later. I don't know if there is a question online. Let me check.
You know, when I question, I ask one question. Something like, what are the next steps you are trying to do after?
Actually, right now we are making some experiments to test the specificity of the sensor by testing the secondary antibody and checking if the secondary antibody doesn't bind to the surface or doesn't bind to the captured antibody and reduce insensitive interaction and affect our measurements. And yes, there's a lot to do. There's still a lot to do, but it's the step that we're currently working on.
So, when you look at, and you know what happened with this possible potential thinking on this secondary antibody, and you see that it could be possible to transfer to any other kind of sensors, other type of biosensors. I mean, you think that should detect other kind of proteins or whatever it's possible to do in this sandwich structure?
Yeah, definitely. Of course, for each application, you need to test the necessary interaction with the antibodies that you are working on, with the analytes that you're working on. Yes, definitely the strategy, we think that it could be applied to detect any type of biomarker.
Any other question?
Yeah, one question. How sensitive is your device to pH or temperature?
We know that LMR biosensors are very sensitive to temperature and to pH, but we work with a buffer, PBS buffer, and so the pH value is established, the value of the buffer, and anyway, we also use the same buffer as reference to measure the achievement of the resonance. So it doesn't matter, for example, in this case, the protein is dilute in a BSA solution that is made in water. It's made in water. So water has a different pH than PBS. And it doesn't matter because it has a different interactive index. And it doesn't matter because then we pass again the PBS, so we can compare the position of the LMR at this point compared to the previous step.
Thanks again to the speaker. Now, we are going to continue with our next speaker. We are ahead of time. It's very good, so you have more time to talk to me and also to our last speaker, Smetana. You have plenty of time to talk. So our next speaker will talk about printed optical sensors for breathing detection and temperature measurement. And she's Rebecca Davila Galeana. She's also a PhD student at the Public University of Navarra. So please, Rebecca. So you need some water.